In part A, we determine the velocity of the particle. So we write the velocity of the particle v of t, and this basically equals the derivative of the position function, that is s prime of t. And this f of t represents the position function s of t. And so we find the derivative of s of t, that is t e power negative t by 2. We find the derivative of this expression. And so here we can apply the product rule to find the derivative of this expression. So consider the first one as t and the second term as e raised to the power of negative t by 2. So first I write down the first term as it is, multiply with the derivative of e raised to the power of negative t by 2, which is e raised to the power of negative t by 2, and then apply the chain rule to find the derivative of negative t by 2. And the derivative of this negative t by 2 is negative 1 by 2 times the derivative of t is 1. So it is negative 1 by 2. So multiply this with negative 1 by 2. Now write the second term, e raised to the power of negative t by 2, multiply with the derivative of the first term. The first term here is t. The derivative of t is 1. We can simplify and write this in factor form. We have e raised to the power of negative t by 2. So let's factor this e raised to the power of negative t by 2. And then I write this first one. So here it is 1 times of e raised to the power of negative t by 2. So I put 1, and in this expression we have t times of negative 1 by 2, which is negative t by 2. So we have written this velocity function in factor form, which is the expression on the right side. In part B, we determine the velocity of the particle after 1 second. So we plug in t equal to 1 into the velocity function to determine the velocity after 1 second. So therefore we get v of 1, and this equals replace t by 1. So it is e raised to the power of negative 1 by 2 times 1 minus replace t by 1, which is 1 minus 1 by 2. And so this can be written as 1 divided by e raised to the power of half, which can be written as root e times 1 minus half is half. And so this equals 1 over 2 times of root e. We put this into the calculator to find the numerical value, and we approximate to 2 decimal places. We get this one as 0.30. This is in feet per second. And so this is the velocity of the particle after 1 second. In part C, we determine the time when the particle is at rest. The particle will be at rest when the velocity equals 0. That is, when v of t equals 0, the particle is at rest. So let's replace v of t and determine the value of t. V of t is e raised to the power of negative t by 2 times 1 minus t by 2, and this equals 0. Solving this, we will get e raised to the power of negative t by 2 equals 0, or 1 minus t by 2 equals 0. Let's solve this first. We get t by 2 equals 1, and so this gives t equals 2. So we can see that at t equal to 2 seconds, the particle is at rest. If we try to solve this one, this will become 0 only when t approaches infinity. That is, for only for larger values of t, this exponential function will become 0. So we can ignore this value of t because it is indefinite, and consider only this value of t, which is this one is in seconds. So when t equal to 2 seconds, the particle is at rest. In part D, we determine the time interval when the particle is moving in the positive direction. So for that, we have to prepare a sign chart for the velocity function. and determine its sign. And whenever the velocity is positive, we see that it is moving in the positive direction, and whenever it is less than 0, it is moving in the negative direction. So for that, let's prepare the sign chart. We have already determined that velocity is 0 when t equal to 2 seconds. So we are going to create the number line considering the velocity is 0 at t equal to 2 seconds. So let's mark this t equal to 2. This is in seconds first. And we are going to take some random values to the left and to the right of t equal to 2 seconds. Let's say if we consider t equal to 1 second, this is for v of t. So let's use the velocity function. This equals e raised to the power of negative t by 2 times 1 minus t by 2. I'm plugging t equal to 1, which is to the left of t equal to 2 seconds, into the velocity function. So when we do that, we get v of 1. This equals e raised to the power of negative 1 by 2 times 1 minus 1 by 2. And we have already determined this v of 1 in part B. So this one is approximately 0.30, which is positive. So here it is positive. We can mark it here. And let's also check after t equal to 2 seconds. So let's plug in t equal to 4 seconds into the velocity function. That is, we determined v of 4, and this equals e raised to the power of replace this t by 4. It will be e raised to the power of negative 2 times 1 minus 4 by 2. Clearly, this is negative because this 4 by 2 is 2. 1 minus 2 is a negative. This is a negative quantity, and this one is a positive quantity because e power minus 2 is 1 over e square, which is a positive quantity. So positive times negative is a negative quantity. So you can see that to the right of t equal to 2 seconds, it is negative. So we can see that the velocity moves in the positive direction only in the interval from 0 to 2 seconds. In part E, we determine the total distance traveled by the particle in the first 6 seconds. So we write total distance. This basically equals the integral of v of t dt from 0 to 6 seconds. We know that at t equal to 2 seconds, the velocity is 0. And from part D, we have also understood that between 0 to 2 only, the velocity moves in positive direction. And after 2, that is from 2 to 6 seconds, it is moving in the negative direction. So we split this definite integral as two parts. That is from 0 to 2 v of t dt plus 2 to 6 v of t dt. And here we find the antiderivative of v of t. We know that v of t is the derivative of the position function. So the antiderivative of velocity function is going to be the position function. That is, this will be f of t. This is evaluated from 0 to 2 plus f of t, which is the position function from 2 to 6. So let's replace the position function, which is t times of e raised to the power of negative t by 2. And this must be evaluated from 0 to 2. Let's replace the position function t e power negative t by 2. And this is also from 2 to 6. This one is from 2 to 6. We now evaluate these values. So first replace the upper bound to here. This will becomes 2 times of e raised to the power of, if you replace t by 2, this will be e raised to the power of negative 1. minus if we put 0 here, this will be 0, and 0 times this exponential quantity will be 0. So I put 0 here. Plus now let's evaluate the second expression. So replace t by 6. This will be 6 e raised to the power of negative 3 minus replacing 2. We get 2 e power negative 1. And we can see that we have this positive 2 e power negative 1 and negative 2 e power negative 1. These two will become 0. And finally, we left with only this expression, that is 6 e power negative 3, or otherwise 6 divided by e power 3. And the numerical value of this expression equals this one is approximately 0.30, and this is in feet. So the total distance traveled by the particle in the first 6 seconds is 0.30 feet. In part F, we find the acceleration of the particle at time t. Also find the acceleration after 1 second. So we write the acceleration function a of t. And this basically equals the derivative of the velocity function, that is v prime of t. And so therefore this equals, let's replace v of t. This is e raised to the power of negative t by 2 times 1 minus t by 2. And so we should find the derivative of this expression. And so once again, we use the product rule of differentiation to find the derivative. Consider this term as the first and this term as the second. So when we apply the product rule, we write the first term and then multiply with the derivative of the second term. The derivative of 1 minus t by 2 is negative 1 by 2. Now I write the second term, 1 minus t by 2. Multiply this with the derivative of the first term. That is, we find the derivative of e raised to the power of negative t by 2, which is e raised to the power of negative t by 2 times the derivative of negative t by 2 by applying the chain rule, which is negative 1 by 2. And so this equals, observe that we have this factor in both terms. That is negative e power negative t by 2 divided by 2. This can be written as negative of e raised to the power of negative t by 2 divided by 2. I'm factoring this, and so when I do that, I get 1 plus 1 minus t by 2, because in the second term we have only this expression. And so this equals, simplify this. In fact, we can write this as a negative of 1 over 2 times of e power t by 2 times 1 plus 1 is 2 minus t by 2. Let's simplify this. This equals negative 1 by this 2 times of e raised to the power of t by 2. Let's simplify this fraction. This is 2 by 1. So this will become 4 minus t divided by 2. And in the next step, we can multiply these two numbers. 2 is 4. So therefore, this equals, we will also multiply this negative 1 into the terms inside the brackets. So it will become t minus 4 divided by 2 times 2 is 4 e power t by 2 is the expression for the acceleration of the particle after time t. Now using this, we can find the acceleration of the particle after 1 second. So we write a of 1, that is we plug in t equal to 1, and this equals 1 minus 4 divided by 4 times of e raised to the power of 1 by 2. And so this equals negative 3 divided by 4 times of root e. We plug this into the calculator and determine the approximate value, and we get negative 0.455. This is rounded to 3 decimal places, feet per second square. This is the acceleration of the particle after 1 second. In part G, we graph the position, velocity, and acceleration functions for the first 6 seconds. So we graph these functions using the graphing calculator or any graphing software utility, and we obtain this graph. That is, this one represents the position function, the blue graph represents the velocity, and the red one represents the acceleration function. And so this is the graph of the position, velocity, and acceleration functions. In part H, we determine the time interval when the particle is speeding up and also slowing down. So we see that the particle is speeding up when velocity and acceleration both are either positive or both are either negative signs. And let's determine this from the graph of this velocity and acceleration functions. We can split this into three intervals, that is from 0 to 2 and 2 to 4 and then 4 to 6. Let's determine the velocity, the signs of the velocity and the acceleration. From 0 to 2, we observe that the velocity is positive and the acceleration is negative. And from 2 to 4, we see that both the velocity and the acceleration are negative. And from 2 to 6, sorry, from 4 to 6, the velocity is positive, and then the acceleration is positive. The acceleration is the red graph, and the velocity is negative. So from this table, this one, let's create this as a table. We see that in this interval, both the velocity and acceleration are opposite signs, which means they are actually slowing down. That is, whenever the velocity and acceleration are in opposite signs, if this one is positive, this one is negative, or the acceleration is positive and the velocity is negative, we see that it is slowing down. So therefore, from the table, we can see that in these two intervals, that is from 0 to 2 as well as from 4 to 6, both the velocity and acceleration are opposite signs. So therefore, we see that the particle is slowing down in the interval 0 to 2, and also from 4 to 6. We write down this in union 4 to 6, and it is speeding up only in the interval 2 to 4, because only in interval 2 to 4 both the velocity and acceleration are having same sign. So we can see that in the interval 2 to 4, the particle is speeding up. We write this in interval notation. So these are the intervals where the particle speeds up and slows down.